various characteristics which are related to the properties of sound waves and the way that our ears perceive them. One of the most important characteristics of notes is their pitch. The pitch of a note is its frequency, called the fundamental. In fact, sound waves carry many more than just one frequency, but this is the most pronounced and distinguishable frequency of the sound wave. We will talk about the others later. Now, sound waves have various characteristics, which are important to the understanding of pitch. In sound waves, the frequency, using the Greek letter nu, is related to the wavelength, lambda, and the speed of sound, v sub sound, by the equation lambda times nu equals v sub sound. Now our ears perceive frequencies, not wavelengths. We know this because we can produce a specific frequency, listen to the sound wave through two different materials, say air and water. The speed of sound will be different for the two materials. The wavelengths must therefore be different for the equation to hold. To the ear, both pitches will be the same. Therefore, we are hearing the frequency and not the wavelength of the sound. Therefore, we know that the pitch will change if either the wavelength or the speed of sound is changed without the other changing to compensate. How might we change the speed of sound? Well, the speed of sound is mostly related to the material through which the sound wave will propagate. The general rule is that the more rigid the material, the faster sound will travel. This is why the speed of sound is faster through solids than liquids, and faster through liquids than gases. With air, rigidity is mostly related to things like temperature and air pressure. However, for the purposes of studying music, the speed of sound is fairly constant, especially for any one performance. Furthermore, most methods of manipulating the speed of sound will allow for the wavelength to compensate, so that the pitch never changes. How might we change the wavelength? The wavelength is a little easier to affect. One of the most common phenomena that effectively changes wavelength is motion. Sound from an object that is in motion will have its wavelength effectively changed by having sound reach its hearer faster or slower, depending on the direction of motion relative to the hearer. You probably have noticed this effect, even though you might have not been aware of what caused it. An ice cream truck, for instance, that plays music will sound out of tune while it is in motion. This is because when it is traveling towards you, the wavelengths are spatially shortened. Since we have not changed the speed of sound, the pitch is going to have to increase to compensate. Similarly, when it is traveling away from you, the wavelengths are spatially lengthened, and so the pitch decreases. This effect is called the Doppler effect. Again, this doesn't have a whole lot of applications in music theory, but it does teach us not to perform while in motion. This would have a possible application, however, on the construction of auditoriums and sound equipment, because materials can change wavelengths by reflecting and absorbing sound waves. Another important aspect of notes is their timbre. Remember that I told you that notes do not carry just one frequency, but many. These other frequencies are called harmonic frequencies, or overtones. They are caused by the method of producing the note. For instance, the method of vibration, or the instrument's material, or shape, etc. All sorts of variables cause secondary vibrations, which appear as indistinguishable frequencies. However, these frequencies are actually quite important. They give each instrument a particular sound, which can be learned and identified. For instance, it is the timbre of a note which tells us whether the note was played by a guitar or a harmonica. If the fundamental was the only frequency produced by the instrument, all instruments would sound the same. Tone falls within the category of timbre, but as musicians, we use the terms differently. Tone further characterizes an instrument by its augmentation to the general parameters that produce the instrument's sound. Another way to say the same thing is that tone is used to notice the smaller differences between instruments of the same type. Take, for example, vocals. Most, if not all humans, have extremely similar vocal systems, with vocal cords and an oral resonating chamber. Therefore, the timbre of the singing is distinguishable from other musical instruments. But there are also slight differences in the construction of everyone's vocal systems. Vocal cords of different lengths or thickness, resonating chambers of different sizes and shapes, etc. These all affect the tone of each individual. Furthermore, a person can change his or her tone by using their vocal systems differently, like using correct breath control. This produces a more powerful and fuller sound. Another example might be how a trumpet can be played with a mute. We can recognize the timbre of a trumpet with or without the mute, but the mute definitely changes the tone of the instrument. Electric guitars are often identified by their tone. All electric guitars have a common timbre, which allow us to recognize the general instrument type, but the tone of an individual electric guitar can often tell us the make and model of the guitar. The two most famous examples of this are the Fender Stratocaster and the Fender Telecaster, which produce different sounds by the configuration of their electronic pickups, among other things. In general, it is said that musicians work on their tone, not on their timbre. The last and easiest characteristic of notes is their loudness. Put simply, this is the intensity of the sound wave. It is usually measured in logarithmic units, called decibels. Loudness drops off as twice the natural logarithm of the ratio of the distances being compared. For instance, doubling the distance will reduce the loudness by about 1.39 decibels. One thing you might have noticed is that decibels use a relative scale, relative to a specific position or loudness. In this way, the difference in decibel levels is far more important than the actual amount of decibels. This is also why home stereos can read in negative decibels and decibel meters at sporting events can read in positive decibels. Decibels only really tell you how much louder one position or loudness is relative to another. A more fixed decibel scale is sometimes used, where 0 decibels is set to the lowest sound intensity that most people can hear.